Thank you
Gracias a
very
todos.
much, Javier. Thank you to all the representative and authorities that have been with us during this presentation or introduction to the Congress. And now let's move on to the next item in the agenda. But before we start with the first presentation, I'd like to share some useful information with you for both the people that are here on site as well as the people that are following us remotely. I was saying at the beginning that we have an interpretation service available, Spanish, English, English, Spanish. Those of you who are in Zoom can see on the right-hand side of their screens that they have an icon that looks like a globe, world globe, and there is where they can select the language of their choice. Also, with regards to questions to the speakers, they will not be done right after the presentation by the speaker, but they will be done at the end of each block of presentations, where there will be a Q&A session, one right before the break or recess, and the other one right before the end of the Congress. In the case of online participants, whenever they want to ask a question, they can use the chat or the actual option of making questions on Zoom. It is important that they remind us when they ask the question who they're addressing the question to. Then my colleagues will tell me what the question is, and then I will make the question here on site. For on-site attendees here, even if we have a good 4G, 5G connection, we also have a free Wi-Fi connection, which is this network that you can see here on the screen. You can connect to it opening your browser in your computer or cell phone. Then you can try to access to any website once you have clicked on the network, and then you will see that by default you will be asked for a user and password. The user and password are the ones that you have on the screen. The event is the 6th Subterra Congress. Well, basically the information you can see on the screen. And the password that you can see on the screen. Let me also tell you we are streaming this on Twitter, so if you want to join us on Twitter, you can do that on the Subterra profile with the hashtag Congress. And that's it. Let's move on now with the presentations. The first group of presentations, we're going to have first Professor Lyesse Laloui, who comes from Switzerland to be here with us. He's an engineer, PhD of floor mechanics and CO2 storage at the architecture, civil engineering and environmental engineering of the University of Lausanne. Also, since 2021, he's a member of the Swiss Academy of Engineering Science. He does a number of things, academic, but he's published 13 books and over 300 articles, and he's recorded 4 patents, which is remarkable. His presentation relates to the performance of a thermoactive tunnel, which is a CEVA project in Switzerland. So whenever you want, Professor, the floor is yours.
So I would like to thank the organizer for this kind invitation to share with you some of the experience that we had in Switzerland related to energy and the ground infrastructure. I'm really very pleased to be here with you. I was invited to give a keynote for the first Congress of Madrid Subterra, and I noticed it since then, all the progress and all interest that is done in this area of using underground infrastructures as a source of energy. So the project that I will tell you about, I was asked actually by the organizers to focus on it because actually it's a good example. It shows you really how is feasible such a project. I would like to thank those who were behind this project. and especially those who are still, or at least worked recently on it. So the project was led by a consulting engineering company in Lausanne, BG, and those who were active in the last part were Dr. Azad Koliji, Mr. Emmanuel Rigaud, Dr. Tawhid Kozarnari, Nima Nimpur, and Loic Lepage. So they were leading those things since 2007, so I will show you all the history of this project. And since 2019, my group joined the effort with Dr. Aliso Ferrari and Dr. Jacopo Zannan. Also, as an introduction, for those who are interested to know more about the details of this project, of course, I will not cover the things in details. I will keep them rather larger in given perspective. So we recently published a paper devoted exactly to what I will present you today, so you can get there the details of the things. So the content of my talk will be first to briefly, even if I'm aware and sure that many of you are very, know about how renewable energy could be used from the ground. So I will briefly explain that again and talk why actually this kind of energy is really of great interest. Then I will focus on energy geostructures to introduce what do we mean by energy geostructures, and after that I devote the largest part of my talk to the case study of this Geneva underground infrastructure. So I would like to start just to highlight why do we need this kind of energy and what is the current situation more or less. So here I'm showing statistics that are coming from European level. They are rather, let's say, old somehow in the sense that they have 4 years time, but things did not change that much. So what we see here is that in the final energy consumption, almost 40% of the energy is used by residential and commercial needs. So this shows already this is a huge amount, very concentrated users of this energy, which is not the case, for instance, if you think about transportation. Sorry, come back. And when we look how this energy is used, and actually we see that 80% of this energy is pure thermal energy. So we are using a large part of it for heating and cooling purposes. We are using it for hot water, and altogether 80% is pure thermal energy. So the answer to this is that what we need basically for 40% of our energy consumption is a thermal energy. So the thermal energy, now if we look from where it's coming at European level, but this applies also, I guess, to Spain in large part also, we see that almost 80% of it, 70 to 80%, is coming from fossil fuel. The issue of fossil fuel you are all aware about is the CO2 emissions. So European Union make a target that in 2020, so last year, to reach at least 20% of renewable energy in its pocket, but actually the numbers are not that optimistic, so there is a lot of things still to be done. In any case, this is a great opportunity to what we call geothermal energy, so energy coming from the ground, to play a role in contributing in providing the entire 20% of the energy needs that I was showing you before. So to do so, especially that we are talking about underground infrastructures, there is this technology that is, we are contributing to its development for almost 25 years now that we call energy geostructures. So energy geostructures is related to the fact that from one side, we have urban and infrastructure development that are happening, so which means that there is building energy needs that are growing. Behind or below this development that we have in the surface, we have development of those infrastructure, underground infrastructures, from which actually we can use all the energy that exists in the ground. So all our underground infrastructures are geothermally activated sources. So all those infrastructures that you see here could respond almost to all the energy needs for the new constructions that we have on the top of them. So in this perspective, I represent energy structures as an interaction between two things: the conventional geostructures, which are all the constructions that we do, could be tunnels, could be foundations, could be parkings. From the other side, we have all the needs for conventional geothermal sources, and with all the advantages that we know: minimum amount of CO2 emissions, renewable energy, available all time, very low cost. So by making the interaction between those two sources or those two components of the engineering approach, we get the energy geostructure. What are we getting with it? We are getting an energy with a very low cost, smart use of underground space, because in any case, this underground space, we will use it for this purpose, so it's a smart way of using it. We are combining the structural underground infrastructure, so construction that we are doing, with the energy that is there. Actually, we are simply using the ground to extract energy, but using also the ground to store the energy. And to conclude this, so we are having renewable energy that is supplied immediately on site to the users. So there is no need for transportation. And as you maybe know, the new regulations at the European level are requesting to have renewable energies produced on site, not renewable energies coming like from hydraulics from other places, or like for wind coming from other places. So it's really a requirement, and geothermal energy with those energy structures is responding to this need. So then we can see different kinds of infrastructures that could be used for energy production. Could be any underground tunnels for transportations, for instance, that we will discuss today. Could be underground tunnels for services. As you know, there could be any underground facilities or any embedded concrete structure in the ground could be used as heat exchanger. With my company, GeoEg, we are developing actually design for several projects. I will not talk about them today here, but just to mention some of those kind of geotechnical or civil engineering structures that could be energy pipes, could be energy diaphragm wall, tunnels, anchors, and we ensure a given amount of energy for each of those infrastructures. So if you are constructing a tunnel, we know that you will get from it something like 40 to 50 watt per square meter of the area of the tunnel. If you are having any underground infrastructure, we know that you are getting from it something like 30 watt per square meter. If you do piles, for instance, we know that you can get something like 100 watt per meter for each pile. Little bit focusing more on energy tunnels and stations, because this will be the topic of the second part of my talk. So here I'm showing some of the activities also that we dedicated especially to those kind of infrastructures. Actually, it depends on the type of the excavation that we do. There are different ways of having heat exchangers. And actually, I'm showing you here the paper that we published after work that we did for the Grand Paris Metro Express. So it's the metro line, the new extension of metro lines in Paris, where we had to develop several kinds of heat exchangers for different configurations and related, as I say, to different technical ways of excavating the tunnels. Let me show you here some examples. Either they are at study of the level of feasibility or they are already constructed and functioning. This is an example of a nice project. This is the second metro line of the city of Rennes in France. So it's an energy geostructure line. It means the tunnel is producing energy for the surrounding area. Well-known Tottenham Court Station in Crossrail project in London, one of the first metro lines with energy exchangers in Vienna, metro lines number 2. Since 2018, I'm working as a consultant for Grand Paris Express project on development of several lines and stations as energy geostructure infrastructures. And since last year, we have a new project in my city, in Lausanne city. It's a new metro line, 6 kilometers of underground tunnel, entirely equipped as energy geostructure, also including the stations. So after this overview, let me now focus on the case study that I would like to share with you. So I will show you basically an overview of the project that was developed. I will show you how the geothermal potential was initially evaluated and how the concept was approved and developed. I will give you also some pictures, some photos. I'll show you how the implementation was done and some practical issues. And then I will rather focus the most about the last part, is that after the construction, after the end of all the project, how the evaluation was done of the amount of energy and also the impact on the geotechnical and structural behavior of the infrastructure. So the project that we are dealing here is, on this line, is a Swiss and French array network line that you see here. So the total length of it is 16 kilometers. The Swiss part is 14 kilometers, and here you have the border between Switzerland and France, and here you have the remaining 2 kilometers. The construction cost from the Swiss side was 16 billion of almost euros. Swiss francs is almost like the euro those days. From the French side was more than 200 million euros. The client was from the Swiss part, this is what will be of interest for us, was the National Railway Company and the Canton of Geneva. So the line here, that it's underground in the tunnel until this station here, that will be of interest for us, and then the tunnel, then the line will be on the surface. So we will be interested by, let me just show it again, by this place here, this station here, that is in part embedded underground because it's the end of the tunnel, and the other part is entering and going to the surface. So this is the place where the station is called Carouge-Bachet, that was considered for this energy geostructure implementation. Actually, it was a joint venture project led by BG Consulting Company. So the project by itself, you can see it here, is about 250-meter long station. So we are dealing just with the station. We are not dealing with the tunnel part, even if a part of it is still at the end of the tunnel, but it's the station here that is used for energy exchange. It has two main entrances. It's made in cut-to-cover approach with diaphragm walls, so I will show you in details later on. And it has a main floor here, and then we have a mezzanine on the top of it. And on the surface, we have the railway lines, and we have roads. So let's start with some historical perspective on how the project was developed and how we reached the stage where we are today. Actually, the primary studies or discussions even started in 2007 based on work that were done at the university levels, so research works that actually were showing the performance already, or at least theoretical performance of such infrastructure. In 2008, so it was decided to run a conceptual study to see whether this is feasible for such an infrastructure. Mainly what I say feasible means implementing in geothermal heat exchangers. In 2009, 1 year after, it was identified, it was shown, and I will show you some results, that there are possibilities and there is a potential for extracting energy from this station. I would say like any station almost in the world and any tunnel almost in the world, there is in all cases a great potential of having significant amount of geothermal energy. So it was here also shown. In 2012, after that, this phase of evaluating the energy potential was validated, It was a need, and this is something that I see in all projects in which I am involved. There is a need of involving an energy company that will take this energy later on and sell it. Without having an energy company involved at this stage is often a complicated process to go further. So we saw that in the Grand Paris Express project, we saw it in Lausanne project. In each time, it's very important to involve energy company from the beginning. So here, the energy company is SCEJ, so it's the Industrial Services of Geneva. So they were very positive and they were very interested by taking this contribution to the project and taking later on this energy and managing its commercial aspect. And with their involvement, the construction started in 2019, and the project was commissioned in started 2012. The project was commissioned in 2019, and after the project was commissioned, the energy company asked us to have a re-evaluation on real conditions after the construction of this geothermal energy station. How much really energy now are we able to extract, are we able to inject, how much amount of energy they could contract themselves on long term. We are talking about something between 30 and 50 years contract. So we had to make this evaluation for them to let them really start the commercial part of the things. So let's now come back a little bit to the early phases. So early phases was a feasibility study. Feasibility study was made by another Swiss company, GeoWatt, based in Zurich, where the idea was to quantify the amount of energy that we can get from such a system. So we are talking about thermal energy. So here we are dealing with thermal analysis. That time it was done in 1D and 2D approaches. It was a sensitivity analysis. However, one has to mention that no identifications was done for the real thermal characteristics of the ground or the hydrogeological related aspects. So this is the reason why a lot of sensitivity analysis were made instead having a real identification on the ground that actually we did later on. So the hypothesis for that were to try to see whether we can use the entire volume of the station. So the area was 230,000 square meters that could potentially be activated, and can already tell you the decision was to do it for the entire of it, and this is what was done. The idea also was to consider what we call a seasonal heating and cooling operation mode, which means that we extract heat from the ground in winter to heat the buildings, and we inject the cold in the ground in winter, and we extract the cold in summer, and we inject the heat in summer. So this is what we call seasonal operation, and there are different scenarios that were considered. I will not discuss them for the moment. So here you see, basically, this is simple analysis, thermal analysis. You have here a finite element model. You define different boundary conditions for it, and you look finally how much you could extract and how much you can inject, depending also whether you consider just conduction process, or if you consider any convection. So there were primary analysis. Among the interesting things also we have to keep from this is the distance of the disturbed temperature or variation temperature in the ground with respect to the walls of the station. So here this is the wall at 0 here of the station, and as you can see, until 5 to 10 meters behind the wall, we are mobilizing an energy there. So this is the volume that will be contributing to the system. So basically, this pre-study was coming to the conclusion that station that is at 14-meter depth, 100-meter long of diaphragm wall might produce something like 250 megawatt-hour for warm energy and 260 megawatt for cold energy. They were the pre-studies of 2012, and then plenty of scenarios were considered, and one of them was about whether the slab had to be activated in addition to the diaphragm wall or not, and based on the results that you can see here, it was decided also to activate the slabs. So this allows to move to the next stage, where it was decided, as I said before, that the total surface of 230,000 square meters was equipped. The real cost, actually, of doing this, that time, we are talking a process of 2008, that time also the Swiss franc was lower with respect to euro, so if you have to transfer the things. So the real cost would be at around, let's say, 80 to 85 euros per square meter of equipping the station. You will see that in practice it was not this cost that was applied, and I will explain it why just in the next slide. But this is somehow the reference cost that was considered. So we will have diaphragm walls that they have a surface of 4,200 square meters, and we have a slab that has a surface of 3,400 square meters. So this is the entire area that is equipped as heat exchanger. So this gives a capacity of around 200 kilowatt. The added cost that was needed for this implementation, you see it here, and it is higher than what we could expect actually for such project, because actually the contract for the construction was already established before it was decided to add the energy geostructure system, to add all the tubes and all the collectors and so on. So in that case, it was not anymore a call for new contractors for having to make the construction, but rather to use the same contractor. And in this case, you have to add something to an existing contract, and the cost was almost the double for this reason. So after deciding to go for the construction, so the construction started in 2012. You see here some view of the construction of the diaphragm walls. You can see here some of, if I have the mouse, okay. You can see here some of the tubes that are put inside this sample cage. Here are the tubes. They are very conventional tubes. They exist two kinds of diameter worldwide, actually, for those infrastructures that you can use. So here is those that were used. So you see here a technician putting the tubes inside the cages. And this is a system that was put in place to get some references point for the collectors. The collectors are those elements that you see here. And you see how the tubes were put with respect to the cage. Very technical, but something entirely feasible exercise that could be done. So, and then, as I was mentioning, so you see well here now the tubes inside the cage. It's not something that delay the construction at all. In all projects, the experience is showing that we do not have delay of more than 15 minutes with respect to conventional construction sites, so it's not an issue by itself. Here, single cage that is put on site, so it's already equipped, and here a double cage element, so it's completely feasible. The same thing as soon as we put all the elements, we have to collect all the tubes in collectors, like those that you see here. So we collect them, and then all of them are led to the heat pump. Same things with the slab. So you see here the tubes inside the slab that were put. So you see the date of the picture in 2013, the collectors for the slabs, and the final collectors. Few words on the challenges and the implementation in this project. Actually, as I mentioned earlier, so there were limited choices for the implementation of the geothermal loops, because the contract for the civil engineering side was already signed, so this had necessarily impact on the cost. But no delays in the construction by itself. So yeah, the only issue, as I said, is the cost. In terms of construction, I found it was a little bit too conservative to limit the length of the tubes to 100 meters. I think in other projects we can go to 200, almost 300 to 400 meters length for each tube. Not more for sure, but 100 additional effort and cost, so I think is not necessarily justified. Then you have, of course, some constraints, no exit for pipes and collectors on the public zone, for sure, for do not allow to have any degradation later on of the system. There are some technical aspects in the design, so for instance, the spacing of the piles and so on, but this is not that important because it's well handled and well mastered. There is a system for quality control that is imposing a minimum loss of pipes during their casting. So actually the operation was very successful, very limited damage. So this is something also, it was a very positive aspect to consider. So as I said, the project was commissioned in 2019, and that stage it was the energy services of the city of Geneva who was in charge of managing the infrastructure, the energy component of the infrastructure, and then, so they asked us, actually we offered them also at the same time, so it was coming from both sides, to quantify in a precise way the amount of energy that they could really rely on in their contract, and also the impact in terms of structural and geotechnical aspect, as those aspects were not designed in the project initially. So the entire design of the station was done considering constant temperatures without considering the geothermal activation. So this mandate that we had several goals, of course, to understand the thermal potential of the installation, to quantify thermally induced mechanical actions on the wall, to define future scenarios for geothermal exploration, because this was very important for them. So what we did in situ analysis to really get information on the material parameters, really how much the potential of the ground was really, and also the potential of the station in each architecture was really. And also we tested geotechnically and structurally the behavior of the diaphragm walls to ensure their safety from those perspectives. So we started by thinking, of course, as soon as you talk about getting material, especially thermal material parameters, we think about the thermal response test. So this is the test that is commonly done for design parameters for ground source heat pumps. The point is that this test is very well known. So for instance, here you see a picture of a system that we developed, at least in our group, many years ago, but there are several commercial systems similar around the world. The point is that this system is very well established for getting parameters when you have a geometry that's a line source geometry. For instance, like you having piles. When you have a station, getting geothermal characteristic of station, actually we discovered that nobody did it before. So there were, I say there were because now we established ways to do it. There were no ways to do it, and nobody tried to do it before. So we started by using our system in a given way that I will explain you. So here we are in the mezzanine of the station. So we put our heating system, the thermal response test, and then later on we change it and we use it a heat pump, water-air heat pump. So this allows us from one side to control temperature, injection, extraction, and the other side to control fluxes, heat fluxes. So this, and then we connected to the network that it was in the station that you see here, for instance, with this exchanger. And in addition, we put transducers. You can see here we have thermal transducers, air velocity. We'll see them again later on. We put transducers for deformation. Here we see them just horizontally, but actually we put horizontally and vertically. So our monitoring system was based on strain gauges for deformation. Here, as you can see here, vertical and horizontal. For temperature, you see the points. For air velocity, very important component, the air velocity, because usually in tunnels or any areas like parkings, tunnels, infrastructure, the air circulation could contribute almost to 50% of the added energy in the system. The ground is 50% in general, the air circulation is another 50%. So this is more or less global values. So we were interested to know the value of the air circulating. So you see here one of our technicians putting the strain gauges, putting here the temperature sensors and the air velocity measurement. So, and we were giving the possibility to test the station during 6 months. So we started 6 months earlier, and then 6 months before the opening of the real commercial activities of the railway line, and then we continued after that. So the measurement that we started to do, so for instance, we started with looking to the temperature evolution inside the station. So I'm having some issues with the mouse. Okay. So here you have the temperature evolution at different positions in the station, compared to the real temperature outside the system. So more or less, you see we are between 20 degrees Celsius and we go down until 0. And we did airspeed measurement system, during the train circulation. And there it was somehow the disappointing part in terms of funding, in the sense that actually there is a linear relationship between the air velocity circulation or air velocity and the heat exchanger coefficient. It's 1-to-1 more or less until velocity of something like 20 meters per second. And in general, when you have trains, we expect to have something like 15 to 20 meters per second, which provides a really great amount of energy. Actually, in the architecture of this station, I don't know whether you notice it, they put here a glass wall that actually make isolation between the train circulation that is happening here outside and the system and the wall. So it makes that at the end, the amount of air circulating close to the wall was rather small. We were about 1 to 2 meters per second. So you will see later on why actually the main contribution of energy for this project was coming from the ground. So I'm mentioning that, so there are no guidelines for thermal response tests that were existing for underground energy infrastructures. So we had to develop them. And among the technical things that I would say that we came with is that the fluid circulation phase should last enough long to cover day and night. Because contrary on those who are familiar with energy piles, actually where the temperature is constant over the week, I would say, or over the year, because actually the ground is not changing that much temperature. Here, the fact that we are having air circulation, so we are in contact with the outside temperature, so we have in the analysis to cover this in the right way. The heating phase should be enough long to ensure the steady state in a system that is very transient by nature. And then there are some typical and practical aspects. But in any case, as soon as you design your testing, monitoring approach, then you need to have a back analysis based on numerical tools, so there are no analytical solutions for such configuration. So basically, I'm showing you here one of those results of thermal response test. So we start here first phase. So here we have the temperature and the time for it. So we start first phase to get the ground temperature. Then we heat the system. We have a transient phase for some days, and then we reach the steady state system. So then the ground undisturbed ground temperature is about 14.6 degrees Celsius, and we were able, with the 1 kilowatt for the duration of some days, to reach the stage that allow us later on to make the analysis to get the material parameters. And then we move it in using a heat pump system, because with the heat pump system we are designing exactly the real conditions, and even most probably it will be the same kind of heat pump that will be used by the energy company. So in that case, actually, we had two models. The first one, we inject heat, so it means that we extract cold, and in that case, we put a limit to do not inject heat higher than 50 degrees Celsius, and we were having this cyclic heating and cooling approach, and from that we come with the level of -7 kilowatt in the heating system. And the cooling test, which is where we extract heat and we inject cold, we limit it to 0 degrees Celsius, the temperature that we inject in the ground, which is rather conservative, I would say. And in this case, we got an average thermal power that is extracted of 2 kilowatt. So with those data, we built our 3D finite element model that allow us to take into account all the physics and all the parameters and boundary conditions to get the real energy parameters of the station and the ground. So in those conditions, we had to kind of train our model on a long-term process. So we started from almost the construction of the station, started from 2009. From 2009, the consideration of the temperature exchange, and with this we were able to have all the scenarios of the dissipation, the evolution of the temperature in the ground at different dates and times. So basically there are two scenarios that are of interest to share with you. The first one is that when we are heating, what we see here, this is the profile, you have a depth, and this is the amount of, this is the heat flux. So the anterior part, that is the other side of the wall that I mentioned before, that from which we can expect to have an energy by convection, that one is not that much contributing to the system, while the largest amount of energy is coming from the ground. So it's the extra dose part. So 80% from the energy exchange was with the ground, while 50% only were from the tunnel. From the other side, when we deal with cooling, but in altogether, the amount of energy that we are getting was really significant. You see, it was between 50 and 70 watt per square meter, which is a rather very high level of it. In the cooling phase, also the level was not that bad at all. We were between 25 and 35 watt per square meter, and then you multiply this by the entire area to get the total amount. And here again, 90% of the heat exchange was coming from the ground, and the part of convection was limited. Quickly now, just to say that from this, we were almost able to get the material parameters for our design, let's say, if you say this, but actually it was not that easy like that, because we are looking for two parameters mainly. thermal conduction for the ground and thermal conduction for the concrete, and we were not able to get a unique solution. So we came with a set of parameters that were used. And then we tried to check whether our analyses were valid by comparing our numerical analysis results that you see here on the left side with the thermal measurements that we did on site with the thermal camera that was allowing us at different positions. So those red aspects, those red slots that you see here are related to given temperature. For instance, here we were having temperature of about 19.6 degrees Celsius that was compared with temperature at the close place, and more or less we were getting the same values, the same values in different places, different occasions. You see here different elements of the diaphragm wall all heated with the given temperatures, and the model was giving each time almost the same values to 1 to 2 degrees Celsius difference. So this showed us some confidence in our model. So from that, we considered several scenarios for the energy exploitation of the system. So either what we call sinusoidal, the same amount of energy for winter and for summer. This is mainly what we do with the new residential buildings. This is scenario one. Then apartment, office, thermal needs, and some optimization and so on. Because as soon as we have the parameters, we are able to design any scenario. So we built a new 3D model for the entire station where we simulate all the tubes that we have in the station. We simulate the circulation of the fluid in the tube. We simulate the type of, depending on the Reynolds number, depending on the velocity, and so on. And we put some limitations to our system, as mentioned before, not higher 50 degrees exchange with the ground, and no lower than 0. We have a velocity for air circulation and the maximum change in temperature and power. So with those constraints that we put on the system, we were able to show actually we can increase the winter operation, which means heating, by 25% if we inject in the summer. And we can use also the ground as what we call a thermal battery. So you can use the ground to store energy. In that case, it allows also to improve the amount of energy that you can get from it. And we came with the fact that this station, so we are talking just about one station, could allow to provide energy to thousands of square meters of surfaces. I will show you in the conclusion the exact numbers. So it was really a very good surprise for us. That said, we had to look now how the thermal gradient, and this is the last part of my talk, how the thermal gradient affect the structural and geotechnical aspect of our structure. Because basically in the structure we have soil, we have a wall. Inside the wall we have gradient of temperature that is not that low. You see between 15 and almost 40 degrees Celsius. This delta T, we have it in winter, we have it in summer. So the idea is we have not only thermal deformation and stresses, but also the fact that we have a gradient, so they are not homogeneous. So we measured the temperature, we measured the deformation of the wall and use it just by changing the temperature. So you see it here. So at different dates, either we are in heating system or cooling system, so we were able to know how much was the deformation of it and how it behaves in terms of dilatation or shrinkage, depending whether we are heating or cooling it. And to make the things simple in the presentation, I would say basically what we see, we have a thermally induced compression and bending in the wall, and we are having thermally deformation or stresses in the ground. So to do things rather in a simple way, we developed an analytical method for all those planar geothermal structures in which we have this energy exchange that we published in the reference that you see here. And we used those things to compute the amount of deformation that is induced in the system. And basically, we try to analyze the things at serviceability limit states. And the results were, first, we have from vertical behavior, we observe a settlement that is induced by the mechanical actions. And the horizontal behavior, we have thermal actions that are acting as a bedding on the wall. However, in all cases, the recorded values are really very low with respect to the Swiss norm or the Euro codes, if you prefer. So we are really in the safe side of it, even if the things were not designed for that. From the thermal aspects, we had those numbers that I'm showing you. We had a deflection that was rather small of 1.5 millimeter. We had the bedding moment that was developed in the structure and the shear force that you see here. So let me now conclude this presentation by saying first conclusion on this project by itself. So there is really a significant potential that was observed and measured and validated in this station, which is, I would say, very good news for all similar stations for using the energy power for heating and cooling from the ground. The annual production that we evaluated is about 600 megawatt hour per year, which could satisfy something like between 1,500 to 5,000 square meters of residential buildings, depending on norms and so on, but this is the size of what we observed. From thermomechanical perspective, the structure being very stiff, so we had high mechanical capacity, so it was really able to absorb all the internal actions that were induced by thermal mobilization and displacement. And the more general conclusion, I would say, about energy geostructures, I think it's a good way to combine structures that we are constructing in any case, so those infrastructure we are constructing them, to add to them a geothermal role to extract energy and to store energy in the ground. It's really reduced costs. All comparisons that we are making with other technology shows that we are really on the cheapest side, if I have to say it in this way, with the possibility really to supply this energy immediately to the customer. So as to conclude, is very smart use of underground space as renewable energy, as we heard it before in the introduction, that now with this new rules or law in Spain, where really the energy from the ground is seen in a positive way, so really this technology allows to have it in that way. And this is a picture of the station, how it is today. Thank you very much for your attention.